We are starting a topic electricity. So there are two types of charges. One is a positive charge, one is a negative charge. So when we discuss about the charges in conduction in electricity, positive mean loss of electrons and negative mean gain of electrons. Okay, so there are two types of materials. One type is called conductors and the second type is called insulators. Conductors are materials they allow electricity to pass through. Why they allow? Because they have free electrons. Okay, so these free electrons are also called conduction electrons. So if we talk about the conductors, metals are good conductors of electricity because they have a plenty of free electrons to conduct the electricity, whereas insulators, they don't allow any current to pass through. Example is plastic, you can take. Okay, and there are many other examples like wood, etc., because they don't have any free electrons. So we are interested in conductors, and we should know that conductors are materials, they have free electrons to conduct electricity. Okay, so we are going to discuss about flow of electrons. So let's define the current. Current can be defined as rate of flow of charge, and charge is electron. Okay, so it is a rate of flow of charges. So current can be written as current is equals to charge per unit time, or current is represented by I, charge is represented by Q, and time is represented by T. So current is measured in ampere. Ampere is the unit. So as shown, ampere is equals to charge per time. So 1 ampere is equals to 1 coulomb from the charge and second from the time. So 1 ampere is equals to charge per coulomb per second. Okay, so there are two different currents. One is called conventional and second one is called non-conventional current. Okay, so let's assume a circuit with a battery or a cell, and there is some resistance attached with it. This is a battery, its positive terminal, and this is its negative terminal. If you take example of a current from positive to negative, okay, so this is a direction of positive charge. Okay, so this is known as conventional current. But in metals, current flow due to the electrons, that is from negative to positive. So this is a direction of flow of electrons. So flow of electrons, that is called non-conventional current. Okay, so there are two types of current. One is conventional, one is non-conventional. So when we solve the circuits, we consider the conventional current, but you should keep in mind that current is actually because of the electrons and they are flowing in the opposite direction. Okay, so talking about the types of current, there are two types of current that we discussed. Generally, one is called AC, alternating current, and one is called DC. So talking about AC, AC is stands for alternating current. Alternating current mean it changes its direction after each half cycle. So if it is moving in a clockwise direction in the half cycle, then the next half cycle it will be moving in the anti-clockwise direction. So if we want to plot it, there is a time on the x-axis and current on the y-axis. The graph will be like this, sinusoidal motion. Okay, one is, this is a positive side and there is a negative cycle as well, positive negative positive negative. And when talking about the DC is direct current. Why it is called direct? Because it flow in the same direction for all the time. Okay, it will not change the direction. So if you want to plot DC, there is a time on the x-axis and current on the y-axis. The DC current will be like this. Okay, it will be either on the positive side or it can be either on the negative side, but it will not alternate its cycle. That is why it is called DC. So how we can measure the currents? For measuring current, what we need a ammeter. Ammeter is used to measure current. Okay, and the symbol for ammeter is this, and it is installed in series with the component, okay, where you want to measure the current, where you want to measure current. Okay, so this is about the current. Okay, next term that we need to know in the electricity is e.m.f. e.m.f stands for electromotive force. Okay, its name is force, but it's not a force. Okay, it's something else that we are going to define. So electromotive force is defined as, let's suppose if there are 2 points, let's suppose there is a parallel plate, positive charge and negative charge, and there is some positive charge placed at that point. Let's suppose it is positively charged. Okay, and let's suppose this point is A, and you want to take this charge, this positive charge, from point A to point B. Okay, so if you want to place this charge from A to B, what we have to do, we have to do some work done, because it is not going, it will not go automatically toward the positive terminal. Okay, so we have to do some work done, we have to provide some energy. So we have to provide energy, to transfer this charge from point A to point B. That energy provided per unit charge is known as the EMF. So EMF is defined as energy provided per unit charge. Okay, that is the EMF. So EMF can be written as EMF is equals to energy provided per unit charge. Okay, so energy provided is by the battery. So EMF is basically EMF is source of what? Source of energy per unit charge. Okay, it is provided by a cell or battery. Okay, so when you see the sign like this is a sign of cell plus minus, and there will be written 12 watt to 20 watt something. This is basically the EMF of the cell. Okay, so it is measured in units of EMF is volts, symbol is V. As we know, EMF is equals to energy divided by charge. So for energy, what we have for energy, we have joule, and for charge we have coulomb, and EMF is watt. So we can write that 1 watt is equals to 1 joule per coulomb. Okay, so next term is potential difference. Okay, so people mostly confuse the potential difference and EMF. So you should know the difference and similarities between them. There are some differences and there are some similarities between the EMF and potential difference. Potential difference is, let's suppose I'm taking the same example. There is a positive plate, there is a negative plate, and there is a charge. Let's suppose it is positive. It is placed at point A and you want to take it at a point B. So what you have to do, you have to provide it some energy. So energy will do a work done. So this charge will do some work, traveling from this point to A point to B point. So the work done per unit charge is its potential difference. Okay, so there is a difference between the EMF and potential difference. EMF was energy provided per unit charge. So EMF was a source. When you provide energy to something, that will do some work. So the work done in the result of that energy will create a potential difference. Okay, so potential difference is measured by the work done per unit charge, and EMF is measured as the energy provided by some battery or some cell to move a charge from one point to other point. So potential difference is same. If potential difference is also measured in volts, work and energy have same units. As we know, it's joule, and for charge it is coulomb. So it is potential difference is 1 watt is 1 joule per coulomb. Okay, so it's more or less same, but you should know EMF is the cause that create the potential difference in the circuit. Okay, if there is no EMF, there will be no potential difference, but for EMF, potential difference is not required. Why? Let's suppose if you have a battery placed at that point with terminal, this is positive and this is negative, it have a 12 watt EMF. Okay, even if it is not attached with the circuit, it have EMF. Now EMF is basically the energy it can provide. So the battery have a energy that is stored in the form of chemical, but when it is attached, there is a circuit and there is some resistance. When that circuit is attached with this battery, then it will create a potential difference across this resistor. So that potential difference is created because of this EMF. So EMF was the cause, and that creates the potential difference in the circuit. Okay, so next we are going to discuss about the Ohm's law. Ohm's law relates the potential difference and the current with each other. Let's suppose, taking the same example, there is some battery and there is a resistance whose value is R, and there is its positive and negative. Its potential is V, its EMF is V, let's suppose. Okay, so and due to this voltage, the current will flow. The current is I. So if I double the voltage, the current will also be increased, and if I decrease the voltage of the battery, the current flowing through the resistor will also be decreased. So it's mean potential difference is directly proportional to the current. So we can say that V is directly proportional to I, and when we remove this proportionality sign, there comes equal and a constant. That constant is R. So V is equals to I R. This is Ohm's law. Okay. So here comes a new variable that is called R. R is resistance. How we can define it? Resistance is basically opposition to the flow of current. Opposition to the flow of current is called resistance, and it is measured in Ohm's symbol is like this, and R can be written as V divided by R. It is derived from the same relation. Okay, so 1 ohm is equals to 1 watt per ampere. Okay, so if you want to plot a graph for Ohm's law, we have a x-axis. On x-axis there is a current, let's suppose, and voltage is on the y-axis. The graph will always start from the origin, and it will be a diagonal straight line. It shows that V and I are directly proportional, and if you find the gradient is basically rise over run. On rise you have a voltage, and on run you have a I, so it is V over I, that is equals to R. So gradient gives you resistance. As the gradient is constant, so the resistance will also be constant. Okay, so if this is about the resistance. Okay, how we can calculate the energy or the power in a circuit? If you want to calculate the energy of a circuit, energy is simply electrical energy. Okay, electrical energy can be calculated by relation. Energy is equals to V I T. It's a product of voltage, current, and time. Okay, if you have a voltage, you have a current, and you have a time, you can find the energy, electrical energy. Okay, I'm not going into the derivation of this relation. You just need to know the final relation, that energy is a product of voltage, current, and time. Okay, and for electrical power, we know that power is energy divided by time. If you consider the above equation, energy divided by time, take this time on the left side, we will get V into I. So that is our relation for P is equals to VI for power. Okay, this is the first relation. We have two different relations for power as well. We can put V is equals to, this V is equals to IR. If we put this, then we will get P is equals to IR, and I is already there, so it will be I square R. This is also power. This is used for power loss, and we can also calculate another relation by putting value of I. I can be taken as I is equals to V over R. That is also from the Ohm's law. So it will give us P is equals to V over R, and there is a square and R already. It will give us V squared divided by R. That is a third relation. Okay, so there are three relations of power that we can use. Okay, all these relation, in first relation we don't have R, there is absence of R. In second relation there is absence of potential, and third we don't have current. Okay, so we can use any of this relation according to the given data and the given scenario. Okay, moving toward the next part of this chapter, that is circuits. Circuits can be in series or they can be in parallel. Okay, how we can identify the series and parallel circuits? Series circuits are in a way that the components are attached end to end, where let's suppose this is R1, this is R2, this is R3. Okay, so there is an end of R1 and that is the starting point of R2. This is the end of R2 and that is the starting point of R3. So they are attached end to end, one after the other in a line. Okay, that is called series. And when you talk about the parallel combination, they will be attached in face-to-face combination. They are facing each other. Okay, so this is a parallel combination. And there is another key point that you need to keep in mind, that they are attached with common terminals. These are the common terminals. Okay, so they're all attached with two common terminals. And if you consider the series circuit, for R1 you have these two terminals, for R2 you have this one and this one, and for R3 if you see you have this and this terminal. So in series all the components are connected with different terminals. Okay, but in parallel combination they all have the same common terminals. Okay, so that is the difference between series and parallel circuits. So let's talk about the series first. If we discuss the series circuit, in series circuit, consider there are, let's suppose, three resistances, R1, R2, and there is another resistance, R3. Now we are going to discuss how the current, voltage and resistance will behave in this type of circuit, and there is a voltage V. Okay, so in this circuit, let's talk about the resistance first. The resistance will be a R total, will be a simple sum of all the resistances, R1 plus R2 plus R3. Okay, that is a total resistance if you want to find. And for the current, if we want to find the current in this circuit, okay, let's suppose current starts from the positive side of the battery. So this is the direction of current. It will start flowing from this point and it will move from the first resistor, the second resistor, the third resistor, and it come back. Okay, there is only one possible path for the current. Okay, so there is no other path available where the current can go, or we can lose any sort of current. So there's only one possible path. So the current will be this is the total current, and this is same moving through this one. Let's suppose this is I2, this is I3. All the currents are same. So we can say that total current is equals to I1 plus I2, sorry, not plus, is equals to I2 is equals to I3. All the currents in all the components is same. Okay, so this is about the current for the series circuit. Now let's discuss about the potential. Okay, so talking about the potential, that is the total EMF that is provided by the battery. That is the total voltage. Okay, this is the source. This is the source, that is source of EMF that is creating, that creates potential difference across R1, R2 and R3. So this is responsible for all the potential differences. Okay, so total EMF, the energy provided per unit charge, will be divided into three components. One is V1, this will have V2, this will have V3. Okay, they can have same values, they can have different values, it depends on their value of resistance, but their total, their sum should be equals to the source. Okay, let's suppose you have 100 rupees and you have distributed among your three siblings. They can have different money, they can have different cash, but when you add all of the currency, that should give you the total amount that you have distributed. Okay, so the same is the case for this EMF. So the EMF, the voltage we provided, is equals to sum of all the voltage, V2 V1 plus V2 plus V3. This is for the series circuit. Okay, So we are done with the resistance, we are done with the current, and we are done with the voltage. These three things you need to know for any circuit. Okay, now let's discuss the parallel combination. In parallel circuits, as we have discussed, resistances are attached one face to face. Okay, and let's suppose there is a battery is attached. Okay, with it have some voltage. This is R1, this is R2, this is R3. Okay, so starting from the resistance, if you want to calculate R total, the R total for the relation for the R total is 1 over R T is equals to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, this is a relation for total resistances for the parallel combination. Okay, now let's discuss about the current. This is a positive side, this is a negative side. So discussing the motion of current starts from the positive terminal of the battery. Let's suppose the total current that is coming from the battery is I. Okay, when it reached this point, let's suppose this is a terminal 1, junction 1. So there are two possibilities. Some of the current will go this way. This is R3, so let's call this I3. Okay, I3 current will go this way, and the remaining current will go up remaining. Okay, so this is the current that we can say that that was total minus I3 that go this way. The remaining part is going upward, and it reach at this point. Let's suppose this is junction 2. At junction 2 again some of the current will move rightward. Let's suppose this is I2, and the remaining part will go upward. This is, let's call it I1. Okay, so when I1 move from this resistance, it will go downward and it will reach at this point, and I2 is coming from this point. So at this point again I1 and I2 are meeting each other. So there we will have a current I1 plus I2 that is coming at this point, and I3 is coming from this point, I3. So at this point I1 plus I2 plus I3 all combined together, and their sum is equals to I, and they will reach the battery again. So we can say that total current I is the sum of all the currents I1 plus I2 plus I3, because that was distributed in the circuit. Now let's talk about the voltage. If we discuss the voltage, the battery is attached with this terminal. Okay, so if you see along this wire, there is only wire, there is no component between these points. No, so they all the components R1, R2 and the R3 and the battery, they all are attached with this. If you consider this one, battery is attached with this, R3 is also attached there, R2 is also attached there, and R1 is also attached there. So they all attached with the same terminals. Okay, so when they are attached with the same terminals, they will have a same potential difference, they will have a same voltage. So we can say that total voltage is equals to V1, that is equals to V2, that is equals to V3. So they all have the same voltage. Okay, so that is for the resistance, current and the voltage in the parallel circuit. In the next lecture we will discuss about how we can how we can find the current, resistance and voltages in series and parallel circuits, and sometimes there is a circuit that is a combination of series and parallel. Okay, so in the next lecture we will try to discuss some past paper questions, inshallah.